Hi, I'm Colin. In this module, we're going to revise the notion of a function being odd or even. We're then going to motivate the important result that the derivative of any odd function is even, and vice versa. Consider the standard cosine function, f of x equals cos x, which has natural domain or the real numbers. Recall that the right half of the graph looks like this. Now, it turns out that the cosine function has a special sort of symmetry, in that if you reflect the existing graph about the y-axis, you'll precisely get the other half of the graph. This means for any value of x in the domain, if you look at its reflection about the y-axis, in other words, negative x, then their y values are the same. That is, x and minus x share the same y value for all x. We say that the cosine function is an example of what's called an even function. Generally speaking, a function f is an even function if f of x equals f of minus x for all values of x in the domain. And as we suggested earlier, this means the graph of any even function holds the special geometric property that its curve is symmetric about the y-axis. This means if you know, for instance, the right half of the graph, then if you reflect that about the y-axis, you'll get the left half of the graph too. Now, consider the standard sine function, f of x equals sine x, which also has the natural domain or the real numbers. Recall that the right half of the graph looks like this. Now, it turns out that the sine function also has a special sort of symmetry, in that if you rotate the graph 180 degrees about the origin, then you'll precisely get the other half of the graph. This is called rotational symmetry about the origin. This means for any value of x in the domain, if you look at its reflection about the y-axis, in other words, negative x, then the y values at these points are the same but opposite in sign. That is, in summary, these 2 points share rotational symmetry about the origin. Another way to think about it is that by reflecting the original point about the y-axis, and then reflecting about the x-axis, you get the other point. We say that the sine function is an example of what's called an odd function. Generally speaking, a function f is an odd function if for all values of x in the domain, f of x equals the negative of f of minus x, which is the same as f of minus x is equal to negative f of x, via a simple rearrangement of the equation. And as we suggested earlier, this means the graph of any odd function holds the special geometric property that it has 180 degree rotational symmetry about the origin. Or alternatively, if you grab the right half of the graph, reflect it about the y-axis, and then about the x-axis, you get the left half of the graph. Okay, so we know so far that the sine function is odd, and the cosine function is even. However, we also know that if we differentiate the sine function, we get the cosine function. In other words, it turns out that the derivative of the odd function sine is the even function cosine. Amazingly, this is true more generally. That is, if you differentiate any odd function, you will get an even function. And moreover, if you differentiate any even function, you will get an odd function. The general proof of this is beyond the scope of this module, but can be proved using differentiation from first principles. Let's now give an example of an even function whose derivative is an odd function. Consider the rational function f of x equals 1 on 1 plus x squared, which has the natural domain all the real numbers. Recall that a rational function is the quotient of two polynomials. Let's first show this function is even. Consider any x value in the domain of f. Then f of minus x is simply the function evaluated at minus x. But minus x all squared is just positive x all squared. And this is just f evaluated at x. So since f of x is equal to f of minus x for all values of x in the domain of f, we've thus shown that f is an even function. It's important to note that whenever you are proving a function to be odd or even using the algebraic definitions, your proof must be general and not assume any particular value of x in the domain. Let's now differentiate the function and then show that the derivative is an odd function. To differentiate, you may be tempted to use the quotient rule, since it is certainly a quotient function. However, since the top function is just a constant, the quotient rule will be overkill here. Instead, we can use an index law to rewrite the function as the function 1 plus x squared stuck inside the function that raises everything to the power of minus 1. In other words, a composite function. As a revisionary exercise, you should now pause the module and have a go at using the chain rule to show that the derivative is the function negative 2x on 1 plus x squared all squared. Alright, let's now show that the derivative is odd. For any value of x in the domain of f dash, which here is just all the real numbers, once again, then the derivative evaluated at minus x is thus the following. The double negatives then cancel away to a positive, and minus x all squared is just x squared. And so this simplifies to the following. Moreover, since f dash x is just the following, negative f dash x is thus the following. Once again, we have a pair of double negatives which cancel away to a positive, and so we have the following. These are the same expressions, which means f dash of minus x is equal to negative f dash x. And thus we've shown that f dash is an odd function. Hence, in summary, we've shown that the derivative of the even function 1 on 1 plus x squared is an odd function. Finally, be aware that functions don't always have to be even or odd. In fact, many functions are neither. And out of interest, the horizontal straight line y equals 0 that sits on top of the x-axis is actually both even and odd at the same time. Alright, I hope you found that useful. See you next time.